5.1, extreme values of functions, worked out homework problems. For the first, say graph and find the extreme values. So there's not a lot of calculus going on here. And of course, you've got to read the question carefully. There's nothing going on here at the zero. So we have actually a non-continuous function. We graph this. First one's x plus 2, so that's a positive slope, but there's nothing going on here at 0. And it's only at a -2, so cross that out, and it's -2 included. And the second one is -x plus 2, and it is also included. I'm going to make a ludicrously big circle. And then I'm going to miss badly. Straight lines are always tough. Make sure we know that's crossed out. And now we have to answer the question. We have an absolute minimum at -2, 0 and 2, 0. There is no absolute max. Because those are holes up there. Moving forward. Gotta graph this sucker. It's a little trickier. One, two, 1, 2, 3. And from -3 to 0, we hit at -1, but it's a hole. Down 1 over, down 1 over 3, up 1 over 3. Solid point here. I want to make a hash of my straight lines again. Then it's 3x minus 1. So it is a solid dot here, which is impossible to show. So what we're going to do, just make it a small one. And it goes up to, if I plug in x equals 1, 2. And it is an open dot there. A little bit bigger in case we need it. The next one, which I think we do. So we're continuous so far. And then it's -2x plus 4, 1, 2, 3, 4, down 2 over 1, down 2 over 1. And it is closed dot, closed dot. Piecewise function. So we have an local maximum. And I'm going to abbreviate from here on out, which I already started doing. Local max here, because that's everything's sloping away. That's going to be a low, that's an absolute min, it's an absolute max, and that's a local min. Wow, that's a lot to keep straight. Local max at -3, 0. We'll just go right along. Absolute min at 0, -1. Absolute max at 1, 2. Whoops. Local min at 2, 0. It's consistent with the extreme value theorem. Okay. right, so absolute extrema. Looks like I went back and scribbled on these to make them a little darker. That's fine. So absolute min, and we're just looking for absolute, so I don't have to worry about anything else. And it said for the x value, x equals b, then absolute max at x equals c. So my max and my min. And I get to use the extreme value theorem because since it is a closed interval, the extreme value theorem applies. I think I need to say it's continuous too. So yeah, closed continuous. Yeah, I definitely have to say that. Closed continuous. Sorry to run that over there. This one, you're going to have an absolute max at x equals a, and you're going to have the absolute min at x equals c. So here the EVT does not apply. It's not continuous. All righty. Over here, we have not a closed or continuous. Although in this case, I don't really care as much because it's not closed, so we're out of luck anyway. Not a closed or continuous interval. So there's no absolute max or min. And, you know, up here, DVT doesn't apply, but there is a max and a min where it doesn't. So this really isn't the reason. It's just because there isn't. I mean, if this point was higher than this point, we'd have an absolute max. But since it's not closed, we don't have to. And in this case, we don't. Tricky to read and make sure you get it exactly right, but hopefully the practice helped. All righty. Calculus. Use analytic methods to find the extreme values. Okay. So I don't really leave enough space here. Apologies. E prime of x equals negative e to the negative x. When does negative e to the negative x equal 0? Never. So let's check the endpoints. E to the, and we use the original function for this, negative 1 equals e to the 1. That's the absolute max. And I didn't graph this, I really should. Then e to the negative 1 equals 1 over e. That'll be the absolute min. do it again. H prime of x equals 1 over x plus 1. 1 over x plus 1, so it equals 0. Again, no solution, comma, but x cannot equal -1. Technically, can't be less than -1. So we can't put -1 in because that x has to be greater than -1. All right, so that's from the original domain. We have to look at the original function. Can't put a -1 or smaller in here. Doesn't matter. We're from 0 to 3, so we're good to go. But it's a good habit to get into. So check endpoints. ln of 0 plus 1 equals ln of 1 equals 0. Turns out that's an absolute min. At 0, 0. And ln of 3 plus 1 equals ln of 4. It's an absolute max. At 3, ln of 4. Seems kind of silly, but I mean, this is what we do. Secant of x from negative pi over 2 to 3 pi over 2. So g prime of x equals secant x tangent x. All right, notice there are no endpoints up here. These are not equal, so we can't check those endpoints. Oh, by the way, in case you're wondering, hey, you said to graph everything, and I still would, but I didn't graph this because we're trying to use analytical methods. Sorry, I had a teaching moment there. I was waiting for somebody to answer that question. Realized I'm not sitting in front of a class. Secant of x, tangent of x equals 0. I recently told my classes, probably didn't hear me, only care about the top of the fraction. Where's sine of x equals 0? In that interval, x equals 0. And at pi, that's it. Those are the ones we check. Tricky part for people, plug it back into the original. Secant of 0, 1 over cosine of 0 is 1. So since we don't have endpoints, we can't say absolutes. Yeah, it's kind of annoying. We'd actually have to look at the graph and go from there. So we're going to go with a local max. That happens at 0, 1. We'll check that out in a second compared to secant of pi. That's -1, 1 over cosine of pi. Pi is -1, 1 over -1 is -1. So we have a local max, min, pardon me. And I'm going to have to graph secant to make sure I'm happy with my answers. Secant goes off of pi from here to there. So that's here, here, and here. And they keep going over to here. So here. This doesn't exist, and this actually hits here. Right there. All right, so that's a local min at 0, 1. answer key is wrong. And this other one is a local max, unless I just screwed up. Nope, I didn't screw up. Local max at pi, comma, -1. People always ask me, like, well, how can I, just look at the algebra and figure that out? And the answer is you can't. So I didn't use my calculator. I know what the graph of secant looks like, so off I went. Good stuff. All right, off we go. F prime of x equals 3/5 x to the -2/5. 3/5 x to the 2/5 equals 0. No solution. However, x cannot equal 0 because in the derivative cause 0. It's no problem with the domain of the original function. So that is a critical point. We got to go check that out. Can't check -2. We can check 3. And I believe this does the vertical asymptote right there. So endpoints. Can't check -2. It's an open interval on that side. So x to the three to the 3/5 equals something like 1.933. So we have an absolute max at 3, 1.933 and nothing at x equals 0. There's nothing going on there. All right. 0, 0 technically is a critical point. So we actually would call it not a stationary point because the derivative doesn't equal 0 there, but it causes problems. So yeah, always check and play and figure things out. Find the extreme values of the function and where they occur. So we can finally do a little bit of real calculus here. So we take the derivative, dy dx, and even though I shouldn't, I am going to graph a little bit. Looks something like that. Dy dx equals 3x squared minus 2. 3x squared minus 2 equals 0. 3x squared equals 2. X squared equals 2/3. X equals plus or minus square root of 2/3, which is plus or minus 0.816. So what is going on here? That peak is on this side and that valley is on this side. They're both 0.816 over. So the, not absolute, goodness gracious, local max at, and I like to go with precise answers. So negative square root of 2/3, comma, and I got to plug that in to this original function. Well, that one's asking way too much. So I'm going to go with 5.089. And then a local min at positive root 2/3, comma, 2.911. So my graph is terrible. This should be down here. Let's actually do that. It should be like here somewhere. Yeah, do what you gotta do. All right. What's going on over here? I graph it. I think it looks something like this. So just to mess up with the nomenclature, I'll go with y prime, 3x squared minus 6x plus 3. Set it equal to 0. Take out a 3 to make my life easier. X equals 1. Now, I didn't do this over here because I saw the graph and I knew what I was doing. I should have, and I will actually go back and do it. So we've got negative 0.816 and 0.816. Number in between is 0, plug it in here, I get negatives. This is a negative slope. Plug in 1, 3 minus 2 is 1, it's a positive slope. Plug in negative 1, same thing, it's a positive slope. So this is why that is a max, and this is why that is a min, and I know it's absolute because of the graph. So number line it, plug in 1. Nice easy number over here to use is 0. I get positive 3. Another nice number to use is 2. 4 times 3 is 12, minus 12 is 0 plus 3, get another positive. So there's no min or max here. This is actually a point of inflection. Cool. A lot of work. Find the extreme values of functions and where they occur. All right, do I want to rewrite this one? Yeah, I sure do. Let's graph something like this, this, this. So we should end up finding just one max. We'll see. dy dx equals negative 1 x squared minus 1 squared times 2x. Don't care about the bottom. Negative 2x equals 0, x equals 0. Plug it into the derivative. If I plug in negative 1, I get a positive. If I plug in 1, I get a negative. The bottom squared, so I don't even check it. This is a max. So that is a max, and as you can see, it occurs at 0. So what is that max? Plug in 0, we get negative 1. So we get, and that's got all sorts of nonsense going on here. So we would say that's a local max at 0, negative 1. I would like to point out at this moment in time that I'm starting to feel a little more confident in these problems, whereas I sat down to do these and they're just so confusing. But yeah, for those who are like, wow, I really don't know what's going on, yeah, just practice. Comes after a while. All right, let's take a quick look at this one. It looks very similar to the other one, inverted. Which makes sense, 1/3 is an odd power. And over here we have 1, which is also odd, but not a power at all kind of thing. We'll see how it goes. So y prime equals 1/3, 1 minus x squared to the negative 1/3, very naughty. Negative 1/3 to the 4/3. I got to think about this for a minute. Negative 4/3, bring it down, it's 4/3. Subtract 1. Yeah, that's right. Times negative 2x. So they cancel out. We're left with a positive. And my answer key has lots of mistakes in it. All right. And so then we say, well, that's 2x over 3 times 1 minus x squared to the 4 thirds. I've set that equal to 0. X equals 0. Here we go again. This is why this is so important to get it right, because I plug in 0. No, I don't want to plug in 0. I plug in 1. 1 minus 1 can't. Naughty, naughty, naughty. Plug in 2. I get a negative. Cube root, I get a negative. To the 4th, I get a positive. I get a positive over here. Tricky stuff. Plug in a negative 2. I get the exact same answer on the bottom, but a negative on top. So we have a local min. Notice what I said, my answer key was wrong because I was just looking at the graph when I first did this. So you always got to do this properly. Local min at x 0, comma, plug in 0, 1. All right, x to the 4th. Graph it, we get some weird thing like this. What am I at? dy dx. dy dx equals 4, which is 2 times 3 is 6x to the 3rd plus 12x squared minus 18x. Set it equal to 0, and I'm going to run out of space, so I'm going to factor out a 6x, leaving me with x squared plus 2x minus 3, unless I'm very mistaken. And then 6x, x plus 3, x minus 1, x equals negative 3, comma 0, comma 1, negative 3, comma 0, comma 1. Nice. Number line, negative 3, 0, 1. Plug in negative 2 to the derivative. That's big positive. That's big positive. Negative 2, that's a big negative. So I got to actually figure this out. It's going to be negative. 2 times 2 is 4, times 2 is 8, times 6 is negative 48. Yeah, think about this. I put in negative 2. Oops. Negative 48, 48. Might as well do the negative 2. I'll do this one here. And then positive, so that's going to be positive. Plug in negative a gazillion. This number is going to dominate these like we've already learned. It'll be negative. Plug in 1/2. Oh, that's hard. 1/2, 1/4 times 12 is 3. 1/2 minus 9 is negative 6. 1/2 times 1 is 1/8. 6/8 is 3/4, so it's negative. Plug in a gazillion. This is going to dominate, so there we go. All right, it sure looks like this first one's an absolute min. So absolute min at negative 3, comma, I plug that in, I get 57.5, negative 57.5. Absolute local max at 0, 10, I believe. And then a local min at 1, 6.5. Tough, very tough. Oh no, quotient rule, Lordy save me. All right, so if you graph this thing, got this very funky little kind of thing going on. And yeah, the derivative is going to be horrible, but we only care about the top. Low, d high minus high, d low, over. And by the way, a lot of times I will look at a derivative and go, oh, Lord, this is going to be horrible. And then I just get around to doing it. It's not so bad. So let's just set the top equal to 0 and save ourselves some time. X squared plus 2x plus 2 minus 2x squared minus 2x minus 2x minus 2 equals 0. A little combining here, negative x squared minus 2x equals 0, if I'm not mistaken. Factor out negative x, leaving me with an x plus 2 equals 0. I don't like this. I don't like this at all. I don't like the way I drew my picture. So, share screen. Equals clear, clear. Alpha y equals x plus 1. X squared plus 2x plus 2. X squared plus 2x plus 2. Interesting. So I'm not that far off. That's where it belongs. It goes there. Something like that. We get x equals 0, 2, negative 2. All right, to the derivative. The bottom's always positive, so I don't have to worry about that. Top reduced to this. So plug in 1. Negative 1 minus 2, it's negative. Negative. And then plug in negative 1. That's still negative 1. That's positive 2, so positive. Plug in negative gazillion, it's going to be negative because that's going to dominate. So this is actually an asymptote right here. Should go like that. That's an absolute min. That's also an asymptote, which makes sense. The bottom is bigger than the top. Absolute min at negative 2 comma negative 1/2. I got that from plugging it into here. And then an absolute max at 0 comma 1/2. Cool math. All right, find the extreme values of the function. Now, as soon as I see absolute values, it's graphing time. And this one I'm going to try and graph very, very carefully. And this is only from negative 2 to 7, so I don't know why I made narrow there. So let's slow down for a second. So let's see what happens when I plug in 0. 1 minus 5, negative 4. Got it. Plug in 1, 0, 1 minus 5. Interesting. Yeah. Absolute value graphs can get really crazy. So find the extreme values of the function on the interval where they occur. So you got to read that question carefully. Max value is 4 from 5 to 7. By the way, I graphed this on my calculator in case you're wondering where I got all that info from. And then the min value is -4 from -2 to 1. Now this one goes to infinity. That's probably where I made a mistake earlier. Interesting. Comes over here. Sorry for the non-horizontal line. All right, max value is 4 from 4 to infinity. The minimum value is -4 from -infinity to -1. Yeah. Yes, my hands are getting tired. This is hard work. Deal with it. Identify the critical points, extreme values, local extreme values. Critical points are not stationary points. I'm going to distribute this. X to the 8/3 minus 4x to 2/3 y prime equals 8/3 x to the 5/3 minus, surprisingly enough, 8/3 x to the -1/3. So we have to do a little factoring here to see what we get. Let's pull out next to the -1/3. Yeah, I would have gone with the common denominator. Yeah, it works that way too, because this is technically on the bottom. But I'm just going to factor out in 8/3 x to the -1/3. Since that's on the bottom, I don't really care about it. I believe that gives me an x squared, because 1/3 plus 5/3 is 6/3 is 2 minus 1. And then I go, okay, x can't equal 0 because of the bottom here, which is not part of the original. And x equals plus or minus 1. And we want to figure out what's going on here. Can't use 0, bummer. Plug in 2. Positive on the bottom. We do have to worry about the bottom for the derivative. Wow, that's a big deal. We get positive on the bottom, positive on top. So this is a 0 is a critical point, so we have to be careful with that. Because we plug in 1/2 and we will get negative, positive, so we get a negative. Plug in -1/2, we get a negative, negative, positive. Plug in negative gazillion, we get a negative, positive, which is negative. Probably should have graphed this a while ago. Let's see what's going on. Right, so we have an absolute min at 2 spots. -1 comma, plug it into the original equation, and we get out 3. That's +1. -3, I should say. 3 last time. Disappointed. Yes, negative. Oh, I don't trust my brain. Graph could be wrong, the whole works. Is -1 to the 2 divided by 3. +1, that's what I thought. So that's -3, which the graph shows. And at 1 comma -3. +1 squared root of -3. Yeah. And then we have a local max at 0 comma 0. And that is not a stationary point. Critical point. Wow, that's a lot going on. Alrighty, off we go. dy dx equals, leave it, (1/2) 3 minus x to the -1/2, 10 -1, plus 2x √3 minus x. Gonna squeeze this in here to save space. √3 minus x over √3 minus x equals and I think I have to go with a 2 over 2 also. Yeah, 2 and a 2, common denominator. Okay, x squared. I guess I can factor out I'll do that in a second. X squared over 2 square root of 3 minus x, negative x squared, plus 4x 3 minus x over 2 √3 minus x. Equals x over, take the negative out, 2 √3 minus x, leaving me with x minus, took out an x, 4 times 3 minus x. Equals negative x minus 12 plus 4x, 5x minus 12, 2 √3 minus x, x equals 0 and 12/5. X cannot equal 3. Actually, there's a whole 3 minus x has to be greater than 0, all that. We'll just go with 3 and see what happens for now. All right, graph this thing, get this funky little, yeah, I can't put a negative in there, so the biggest I can put in is 3. So that's the original domain, covers that. I can't put in 3 here, I can't put in 3 here, so that makes sense. We go out to about 3 and we got this like zippity-doo-dah thing here. So we have a absolute, if we go back to you, 0, 12/5. That's 2.4. So I got to check something really crazy like 2.5 because I can't go any further than that. So that's going to be into this here. The 2.5, 5 halves, 25 halves, 12.5. That's positive. That's positive. That's negative. Complicated math. 1, negative, positive, negative times a negative, negative a gazillion, positive, negative gazillion, negative, positive. Yeah, we're good. Tricky stuff. All right, so absolute min at 0 comma, looks like a 0, 0. Local max at 12/5, comma, 4.462. I blasted that out with a calculator. A lot of work. All right, and local min at 3 comma. Oh, my graph is wrong. That's so very upsetting. It comes all the way down, hits here. So that is an absolute min at 3 comma 0, because I plug in 3, I get 0 out. And that is not a stationary point. It's an endpoint. The derivative did not equal 0. Sorry about that for writing off screen. Woo! That is a lot of work. All right, off we go. I believe I found a mistake in my notes. I believe it's just supposed to say 3. Upsetting. I just find it very confusing now that I look at it, trying to figure out what's going on. Let's run with it, see what we got here. Plug in 0, 3 equals. So x y equals 3, when x is less than 0. Goes forever down. Sure, whatever. So looking at this, there's going to be a max here. Let's go find it. Y prime of the bottom is 2 minus 2x. 2 minus 2x equals 0. X equals 1. All right. So local extreme values. Absolute, I really should make a habit of doing this. 1, less than 1 is 1/2, because I can't go over there. So 3 plus 1, 4, minus 1/4, positive. And some big number, this is going to dominate, so it'll be negative. Absolute max at 1 comma 4. And then min at y equals 3, according to the way this is drawn. And that'd be a local min. Horrible, horrible problem. Curious how badly I butchered this, but what are you gonna do? Yeah, y equals 3. I suppose I could write it as a parentheses sort of thing. And this is not a stationary point. Whew. Hard work. Almost there. Function models volume of a box, find the extreme values of V. V of X equals X times 160 minus 32X minus 20X plus 4X squared. V of X equals 4X to the third minus 52X squared plus 160X. V prime of X equals 12X squared minus 104X plus 160. Set it equal to 0, 12X squared minus 104X plus 160 equals 0. Man, this is some ugly factoring, but I can pull out a 4. $3x squared minus 26x plus 40 equals 0. Those haven't seen the way I factor things now. 3 times 40, we pull this out. X squared minus 26x plus 120. Then we factor and shove it back in. X minus 6 times 20. X minus 20. And then we bring it back in here over 3 plus X minus 6. And we also bring it in here over 3. We can divide it, we do. If not, we throw it up. 3x minus 20, x minus 2. X equals 20/3. X equals 2. 6 times 3 is 18 outside of this. So at X equals 2, V of 2 equals, plug it back in here and I get 144. All right. There are no endpoints to check because they're not giving us. So different values in terms of volume of the box. So let's find out. I think I sounded way too eager the way I just said that. 2. Plug in 1 to the derivative. This is still the derivative. 3 minus 26 plus 40 is a positive number. Plug in 3. 9 times 3 is 27. Plus 40 is 67. 3 times 26 is bigger than that. 78 minus 67. So that is negative 78. So that's a negative. So the largest volume of the box is 144 cubic units, which I really shouldn't do, but it occurs when X equals 2. Function, models prime rectangle, X by 100X, find extreme values of P. Yes, this freaks me out. I don't know what that means. So P prime of X, 2 plus negative 200 over X squared equals 2x squared minus 200 over x squared. Only care about the numerator. There's different ways to do this. I'm doing it this way. 2x squared minus 200 equals 0. X squared minus 100 equals 0. X equals plus or minus 10. Use x equals 10 because it's from 0 to that. Notice x cannot equal 0. That's fine. It's not in the domain. So function finding extreme values p of, sorry, 10. So plug in 1, 2 minus 200, negative. Plug in gazillion, that gets towards 0, it does go to infinity. And that's basically just 2. The p of 10 equals 2 times 10 plus 200 over 10 equals 20 plus 20 equals 40. All right, what does that mean? That's a minimum. So the smallest perimeter is 40 units. It occurs when x equals 10. So this is a perimeter of a rectangle. Wow, this is just kind of weird. So the dimensions are 10 and then 100 over 10. 10 by 10 square. So if you think this one through, the smallest units are going to happen when you get a square. Smallest perimeter is going to happen when you get a square. If you've played with these numbers before, in problem 4, you see that happening fairly commonly. So, wow, that's a lot of work. Long video. Happy mathing.